In this video, we're going to look at the effect a buffer has on preventing changes in pH, resisting changes in pH, with an example of a common buffer used in biological systems. So we're going to look at a molecule called tris. This is a common base that's used. Tris, the protonated form tris H plus. This is what it looks like. Let me get my HO. H2CH, CH2OH here, CH2OH here, and then we have an ammonia group on the top. All right, and so this is the protonated form. You can take off the proton from here to make the base form. So this is a commonly used biological buffer. The pKa for this protonated form, which we'll need to do our buffer calculations, is 8.072. We can look that up. And let's imagine we have 1 liter of 0.1 molar tris and tris H plus. So 0.1 molar of each of those. So we're starting with a 1-to-1 ratio, which means that our pH will be equal to the pKa, which means our pH will start at 8.07. So it's fairly close to neutral. That's why one reason why this is a very commonly used buffer in biological systems. Okay, so let's imagine we have 1 liter of this buffer and we add acid to it. So let's say we add 5 milliliters of 1 molar HCl. So let's first do this calculation assuming there's no buffer, right? So if we just had 1 liter of water, if we add 5 milliliters of 1 molar HCl, what would the pH be? So 1 liter of water obviously would have a pH of 7 to start. We assume neutral pH. So let's see, 5 milliliters times 1 millimole per milliliter means that we'll have 5 millimoles of H plus and chloride. All right. And so that 5 millimoles, 5.0 times 10 to the minus 3 moles will be dissolved in 1.005 liters. So from that we can find the concentration of H plus. Now with no buffer, obviously we should get a quite acidic solution. So 5 times 10 to the minus 3 divided by 1.005 gives us a concentration of H plus, which is 0.00498 molar. And if we calculate the pH from that, I have my calculator over here on the other screen, you can't see it right now. Negative log base 10 of that value gives us a pH of 2.31. So we can see a pretty drastic change from the addition of a small amount of HCl, which is what we would expect in a solution without any buffering capacity. But now let's see what happens with the buffer. So we have our tris buffer there. And there we go. I thought my screen was frozen there. Okay, so if we have 0.1 moles of tris and tris H plus in our 1 liter. So let's think about what happens when we add H plus. All right, we already calculated that it's going to be 0.005 or 5 millimoles of H plus are added. And what's going to happen to that H plus? So with the H plus, the acid will react with the base. So H plus and tris will react and form tris H plus. Right, that's what's going to happen when we add our tris H plus. So let's think about this in terms of initial. We have 0.005, 0.1, and we're thinking about this in terms of moles, and 0.1 over here. So all of this is going to react. Our 5 millimoles, and we will lose some of our tris as well. Oh, one too many zeros there. and we will add 5 millimoles to this side. And so this will go to 0. Here we'll get 0.1 minus 0.005, and here we'll get 0.1 plus 0.005. So now we know sort of our final values here. If we can plug this into the Henderson-Hasselbalch equation, the pH will be equal to the pKa, 8.072, plus the log of the ratio of our base over acid. Now one trick we can play here, not trick, but one simplification we can make here is that both our acid and our base will have the same volume, and so we can write things in terms of moles. Technically it should be molarity, but the volumes will cancel out, and so we get the same whether we do this in moles or in molarity. So we can just plug in these values that we have over here. So our base is 0.1 minus 0.005, and our acid is 0.1 plus 0.005. We can plug that into our calculator, and we'll get a pH of 8.03. So the pH decreased a little bit, as we'd expect from adding acid, but compared to not having any buffer there, we see it's a huge difference, right? The pH without any buffer, right? So with the buffer, it's 8.03. Without any buffer, adding that amount of acid would have changed the pH to 2.31 instead. So you can see a pretty drastic difference here. One other thing I'll point out is that the final volume doesn't actually show up in any of the calculations here, and that's because those volumes cancel out. So this is an example of how we can look at adding acid, or we can consider adding base to a buffer. This is also how we can adjust the pH of a buffer. By adding strong acid or strong base, we can convert the conjugate acid to the conjugate base or vice versa.